That's all, yes. And with this, we pass the stage to Katerina, who's the chair of the first invited talk, and whom we thank for bringing very young participants to to SAS, future abstract interpretation researchers.
Thanks.
Thank you.
So, good morning, everyone. Welcome to the first session. So we have a keynote and a talk. And the keynote is given by Chang. He's an associate professor at the University of Colorado Boulder and also an Amazon scholar. And he does excellent work in static analysis and with a particular attention to the challenges that bring modern software applications from Android to Objective-C, JavaScript, TypeScript, and so on. I won't say more. The floor is yours. Thank you.
Thank you, Katerina, for the lovely introduction. All right. So thanks, everyone. It's such a pleasure and honor to be here at SAS. It's, of course, one of my favorite venues, and with all of you great folks. This is some joint work with some students, past and present, at the University of Colorado. So this talks about some work over several years now at this point. So, all right. So let's get started. Okay. So we're going to consider one of the most important problems of our times, of course, that unfortunately Angry Birds has stopped. Of course, this is a crash in an Android application. And, in today's modern world, such a crash has significant consequences, right? It's magnified by the crowd. That is, in order to upload your app and get it used, right? You have to put it on the Play Store, and on the Play Store, then you're subject to the reviews and the whims of the world, right? That is. Reviews might say if your app crashes, right? Oh my gosh, it's crashed, it freezes, maybe it's sluggish, and so therefore it must somehow be spyware, right? And that forces, the developer, right, to cry for help, right? To that, I don't know how to fix this correctly, and my boss is like on me to get this done right away, right? Okay. Now, of course, with these big fixes, maybe this is an opportunity for static analysis. And of course, I'm being a little bit silly here, right? That about Angry Birds, but Android is used everywhere from in satellites or in tractors and so forth. But also, we consider it as a model system for thinking about event-driven systems, interactive systems, whether it be Node.js, React, or ROS. Right? Okay, so to look at these challenges, let's ask the expert Android developers. So we found this nice talk on the internet about how Square handles Android crashes. So here's this net summary of the talk, right? One, it's kind of inevitable. It's not necessarily even your fault, right? Maybe the framework has been modified in some way that causes the crash. So what do? Well, you log as much information as you can, so for when it happens, you know something, right? And then you check conditions to maybe crash it early and fast, so that it's more likely that you see it in testing. Right. So my net summary is something like, well, you want to see crashes as early with the best possible history and context information. Right. But so suppose we're lucky and get a crash, now what? Okay. So, well, here's essentially such a crash, in a different app, but like in an open source app. And here's an issue, a very nice issue in this Atenapod app. It's actually, if you're looking for good issues, we found lots of great sort of well-documented issues there in that app. But anyway, here what it says is that, okay, there was a stack trace, right? That there was a crash, there was an illegal state exception, cannot execute this task because it is already running. But why? Okay, so we examine the stack trace, and we find that the only app code in the stack trace is this callback where the framework is already in the legal state, right? But what is the callback that came before that caused this app to be in a bad state? And if you will, that's my summary of what you want to do is log as much information as you can so that you know what might have happened, right? So this is some bug from violating some framework protocol rule, so maybe implicit framework protocol rule that we didn't know about until we saw this crash. Okay, all right, but there's actually more good information in this issue. That there's some discussion here, and well, first, it was actually fixed. In my opinion, like wow, and with this very limited information, it was somehow fixed, right? And then what I pull out here is that, like, well, I haven't really found out how to reproduce this, But this is the only scenario that makes sense. And then goes on to describe that scenario, which is quite amazing, right? That these expert developers have some expert mental model of what callbacks could have come before, right? To understand, just like what is the possible way to fix it? I can fix it because I know what could have been the scenario, what must have been the scenario to cause this crash, right? Right. So the issue is not really, I don't know how to fix this correctly, but actually, I don't know, maybe how we can help as static analysis folks is, I don't know if this fix is really a fix. Can we actually do verification and verify that such a fix is good? Right? So to me, this is the opportunity for static analysis. Okay. Well, let's first kind of get into the heads of like becoming an Android developer. So let me tell you a little bit about Android callback-oriented programming to the best of my ability as a non-Android expert. Right, so you implement an app, some app code, but of course, you're surrounded by the ginormous Android framework, where you implement some callbacks in order to sort of connect with the framework. So when you open your Android 101 textbook, the first thing you hear about is an activity, and what an activity corresponds to is roughly a screen on your application. And so you implement some callbacks to react to events, such as your activity being created, so onCreate, or your activity be destroyed and onDestroy. And then if you continue on in your sort of Android 101 textbook reading, right, then the first thing you hear about is this notion of an Android activity lifecycle. That is, you have a bunch of callbacks that you can register to hear about, like whether your activity has been resumed or paused because maybe your activity has been backgrounded, your app has been backgrounded. Right, so, okay, seems good, right? The control flow in your app is dictated by a lifecycle ordering of callbacks, right? Seems so far so good, right? Okay, all right, so let's dig in a little bit more into this particular issue. Well, maybe you want your app to do something, so you have some button, right? And then in order to respond to the user clicking the buttons, right? Then I have to register another callback, some listener for buttons, like this onClick. All right, so I have to update my diagram here, right? And then I read a little bit more, and I see that okay, an onClick can only happen when its activity, whatever that is active, right? And I guess so. It's somehow the click can only happen inside when the app is between resume and, or when the activity is between resume and destroy. Okay, still so far so good. Okay. Now, so inside this app, there's this like async task execute to start some sort of background task. Okay, and this is actually where the bug happens, is that if the user can click somehow twice too fast or something, and then they'll start this task again, and the sort of protocol is that you can only start it once. Okay, all right, but when your task is done, you have to do something, right? So afterwards, you need to know when it's done. So then you register some other handler for when the execute is done. So this onPost execute. And all right, so now it gets hard for me. I don't even know how to put it into my automaton diagram anymore, right? So I have some onPost execute. Well, it can't happen anywhere. It can only happen once because your task can only finish once. And actually, it can only happen after the executes has been called. Okay, all right. So, and then inside that execute, then, well, maybe when you're done with that, whatever the user's done, or that background task, maybe you just want to shut down this activity, so you make this call to finish the activity. And what we discovered in the course of the work is actually, if you ever make such a call, then there's more edges here that's not even in your textbook diagram of the activity lifecycle. Okay, so what's the net summary of this very long monologue on this slide, right? Is that really the lifecycle framework model gets out of hand quite quickly and is not static. Okay. Okay, so maybe some Android expert developers are in the room, maybe, and might say that, oh, well, we could fix this because async task is like deprecated and not even used anymore, or really recommended not to be used anymore, maybe because of this complication. Okay, but here's another issue. Same app, same expert developer, 3 years later. And this time, using the much more modern RX Android framework for handling such tasks. And it's definitely a much cleaner framework and much more readable code, but fundamentally the same issue is still under there. Okay. All right, so now back to being static analysis folks here, right? So let me pop up a little bit and talk about static analysis for verified software. Okay. Stuff that we are all familiar with. Well, so okay, so you give me a program, right? And we here in this room, right, implement some verifier based on static analysis, right? To then issue some proof or issue report, right? That is, we want to derive proofs that our programs are safe. Here we want to prove the absence of illegal state exception. Right? And we all know that we do that by system examining the program to simulate running on all inputs, right? That is, using whatever favorite techniques, interpreting abstractions, transforming predicates, checking models, inferring types, right? And then all inputs is then, instead of concrete inputs, we use formulas. Right? Okay, so this is the idealized story. But I want to talk about two ugly truths that we sort of tend to sweep under the rug, right? Whether in papers or when we sort of teach students because we don't want to expose them to the sort of dirtiness, right? Okay, one is well known, and actually both of them are known, right? But one is talked about a lot more than the others, okay? The one that's talked about more, of course, is that most of the time we don't get proofs, but we get some issue reports, right, of maybe bugs, right? And of course, this is the well-known, often talked about, right, false alarm problem, right? To soundly get proofs undecidedly necessitates imprecision and the possibility of false alarms. We just hope not too many. Okay. All right, but the other one is that we don't really have the program, do we, right? We have some of the code, right? We might have to like patch it up, right, with library models. And therefore, like, when we patch it up to get the program, right, then, well, we don't know really if we have a proof. Well, again, let's suppose we're in that good case, and our tool said proof, right? We don't know if we really have the proof, right? Right, so to get a system to analyze, we have to somehow model the missing code in our, Swiss cheese, right, to plug those holes, right? So, but unsound models can lead to missed bugs, and we just hope not too many. Right. Okay. And of course, if we think about the context of what we were just talking about in Android, right, of the app, right, it's really some tiny bit of small code, right, surrounded by the big Android framework. And we're essentially saying, oh yeah, we're going to sit down and write that full Android model, right, right. And, and that's really the question that I want to talk about today. Okay. All right, so let me dive in a little bit more, right, and first come back to that kind of textbook picture of we have the program. So this is the basic program analysis assumption, right? That we're given a closed system, then we have main, some textbook closed system, make some transitions, maybe make some more transitions, blah, blah, blah. And eventually, whatever, that is, we're given a transition system, all right? So as a premise, we're given a transition system, and then we compute a fixed point in an abstraction, and we spend all our time thinking about awesome abstractions and stuff, right? Okay, cool. All right. Okay, but again, this in practice issue, right? So we have to somehow manually model the missing transitions, right? For our Swiss cheese, program, right? So, and sometimes those transitions drop out, and there's like, we have to write some library model. Okay, it's painful, but it seems okay. We get pre and post conditions, or use types and so forth like that to get some model for some code that we don't have, that we understand, right? And I guess my first point about event-driven frameworks is really just that. Well, of course, a lot more of those transitions are gone. And we don't even have a main, right? It's just, in fact, that drops out, right? We just have a bunch of these little callbacks, on, resume, on, destroy, on, click, right? And we know that there is some sort of thing about, well, when is this callback possible, right? When is this event-driven callback enabled, right? And, we're missing that main driving, what's called the callback control flow sometimes. Okay, right, so all right, we just have to sit down and write the Android framework model, right? But it's really complex, hundreds of API packages, thousands of API classes, tens of thousands of API web methods, and this is like years ago, and it just keeps getting bigger and bigger, right? And worse, right, this can change from version to version and platform to platform, right? Are we gonna keep doing this, at the speed of, of Android framework updates, right? Okay. So, right. So net summary, right? The enabled callbacks change dynamically. There's too many missing transitions to feasibly model soundly and precisely. Okay. All right. So that's really depressing. Okay. Should we just give up? Maybe we just call it a day or something. Okay, so this talk is about giving some hope. Okay, about starting out with some goal-directed abstract interpretation. Right? So that, given a transition system, what is the premise here is that, okay, well, instead of maybe fully computing that abstraction, right, like what we want is maybe we're given some error goal that we want to refute. That is, maybe not all, maybe we're not going to prove the full program safe, but just this one illegal state exception that we saw crash, right? Right, that execute task can't run, right? That is, we want to prove that this one error is unreachable. We want to provide help in this. I don't know if this fix is a really fix, at least for this particular assertion. Okay, so then if we were just taking that picture, then well, we might kind of like start from there and work backwards and so forth to see whether we can sort of determine that it's not possible, right? It's like the same picture, just backwards, right? Compute a fixed point backwards from error and an abstraction. Okay, but the nice bit is that, well, the rest of the program is completely irrelevant if we only care about refuting this one error condition. But we're still doing the same thing. We're over-approximating backwards reachability from an error goal, again, to contradict the initial condition. And of course, this is not like, this is like stuff that's been going on, in many different places, including stuff that I've done in the past year, right? Of course, that's related to the idea of necessary preconditions, just kind of phrased slightly differently. Right? And of course, it goes back to, the notion of forwards and backwards being complementary and being able to find goes back, long time. To Cousseau in at least 99. Okay. All right. Okay, so if I might digress from the main storyline for a moment, just to kind of dispel with some sort of confusions about this very generic term goal-directed analysis, I guess. I'm focusing specifically about this notion of refuting an error goal. But something that might come up and sounds very similar is, well, maybe you want to witness an error goal. You want to witness a crash, right? And then we're in the world of under-approximations, okay? Which again, I'm not considering today, but of course, there's lots of related work in that space. Very, like under-approximate backward symbolic from way back, but also very hot these days in terms of talking about incorrectness logic, right? Combining over and under approximations and testing and symbolic execution and so forth, right? Sounds very similar, but slightly different sort of goals, right? Okay. There's also like the idea of doing still that sort of forward global proof, right? But maybe refining with some sort of error goal. So to compute backwards to refine a forwards from initial abstraction, right? That we want to refine an over approximation for exhaustive proof while witnessing errors potentially, right? So like kind of change the abstraction somehow, maybe rerunning the analysis after we've learned something more. And of course, this is the idea of like CGAR. I think, in this very global top-level picture, also like PDR, and we've also done some work in using kind of goal-directed thinking, right, in doing refinement. Okay. All right. Okay. So back to the top-level storyline, popping back. So what I want to say is that, well, also this goal-directed thinking enables some targeted modeling of these missing transitions, right? So getting back to our picture, right? It's like in our event-driven framework where all those transitions have fallen away, that, we have our callbacks. Can we just, if we only care about refuting an error goal, right, in the, event-driven framework, right, can we only model these relevant missing transitions? Okay. That is, can we do some sort of targeted or lazy modeling of the callback control flow just to consider just these relevant callbacks? Right, and I think from my perspective, this is essentially what we're trying to do is, in static analysis, mimic what this sort of expert developer, is essentially saying. Right? Okay, so. All right, so for the rest of the talk, right, we're going to take this picture. Okay, and the first bit we wanted to a little bit look at is that, well, if we really are forcing ourselves, we just have app code, then let's think about this app framework interface, right? Can we, think about like, what is that core model if we really only have app code? Can we define a transition system where we just have app code and app-only transition, so to speak, right? Some sort of core calculus model. Okay. And that led us to this idea of enabled and allowed messages, which I'll just say a few words on. Okay. All right. Then I'm actually going to call back to some, much older work of ours, right? In trying to tackle this problem, right? And of the idea of like being able to pick out relevant callbacks. And that led us to this idea of, well, we can do selectively control flow abstraction, if we're given a goal. Right? And that allows us to identify some relevant callbacks. And we sort of define this notion of a relevance relation, conceptually. Right? Okay. All right. Well, then kind of putting those two older ideas together is what kind of led us to where we're at today, right? Of being able to only model these relevant missing transitions. Right? And this idea of abstracting message histories. Which allows us to decouple the temporal logic specification that we might want to make about callback control flow from actually just app-only code analysis that really, really just looks at the app. Okay. All right. Okay. So let's dive in. Okay. All right. All right. So back to our sort of huge, like, Android is crazy picture, right, or something. Right. Let's, for the moment, right, just dive in a little bit more about the craziness, right? Even though we've already sort of convinced it's crazy or hard, right? To just, like, let's just try, right? Can we, do good enough upfront modeling somehow, right? Let's just try to write that pink, picture, right? And, so taking just, this automaton picture, right? It's tempting to say like, oh, let's write, some sort of fake main, some driver, that like, just models that sort of automaton, right? That maybe where the, on create state is where we start, right? And so then, we'd make some sort of, call to the app that we're trying to like model the driver for, right? It's like the on create callback. So that little dot, dot, dot is supposed to try to represent that interface. Right, and then if we were able to do that, and again, this is why this is super tempting, right, is that, oh, well, once I sort of combine my app code with this driver model, then I'm back into the sort of nice, clean, whole program world, and I can just pass it to my verifier, and I don't have to think about this sort of yuckiness anymore, right, this sort of ugly truth. Okay, all right, look, but some things, right, well, okay, I need some activity to call, right, so I need some activity that's from the app, okay. All right, and then I'm in the resume state, right? And then, well, I need some activity from the app. But this is supposed to be the same one, right? This picture is supposed to reference, oh, it's about the same one, right? But now do I have to interleave it with other activities? Okay. All right, okay, but let's just say we do the same, right? Okay, then maybe I, have a choice to go into the on pause or on click state, right? So, but again, like if it's like in the on, so let's say we're in the on click state, right? Then we have, okay, some button, here that needs to go there, or, but oh, do I need it to be all buttons, I guess? Or but it's really all buttons that's attached to this activity, right? So now I need to like take the app again and do some sort of analysis to generate a model to be able to do more static analysis. So, that sounds scary. And then, of course, I have this listener here, this other listener object, for some button from the app, and of course, this state is only possible, after this listener has been registered. So how do I capture that, right? Again, this is kind of the same picture we discussed already, right? That the challenges are there are arbitrary many app instances, right? That the callbacks are enabled dynamically. So I think it's really, really hard to be sound enough, to be precise enough, and to have covered enough. And I've just like touched a couple different sort of framework classes, right? There's nothing about Arc Android here at all. Right? Okay. And of course, we observe this, but we're not the only ones to observe that it's really hard to be sound enough. Right? Okay. So what's the pragmatic approach here is basically just to ignore and say, oh, there isn't no life cycle description or something like that. This is essentially done, as far as we can tell, by all the industrial Android analysis tools. It's just assume every callback is an independent program, right? And then just prove what you can prove there or whatever, right? But anyway, seems like a real need to re-examine callback control flow constraints. Okay, all right. So if we just back up, and just kind of like don't even think about the static analysis for a moment, right? And just observe the sort of concrete framework app interface, right? we make this little picture. Is that, okay, I'm going to draw like a sequence diagram of sorts, right? Like a framework timeline and an application timeline, right? And then let's say, at the beginning, the user clicks some button, the framework receives that, and then issues some sort of on-click callback to the application, so listener to on-click, right? So a callback is where the framework invokes an application method. And then in response, or inside that callback, for example, like the application might invoke some API calls back to the framework. And just by analogy, or we're going to define a term here, right? That a call-in is where the application invokes a framework method, so in complementary. Right? Okay, so maybe that callback is done, right? So on-click returns to the framework, and then another event happens, right? The background task finishes and invokes async task on post execute, right? So now on post execute can't happen unless that execute has happened before, but in this timeline, this is a valid sort of timeline. Right. Okay, so anyway, this picture says role. Yeah, the event-driven framework uses callbacks to notify the application of events, and the application uses call-ins to affect how the framework invokes future callbacks. Okay, and just so that I don't keep saying callback, call-in, blah, 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 right? Because it's really just generically this sequence, right? I'm going to define a term messages to be either callback or call-in invocations with these actual arguments, with these actual concrete instances. Okay, all right. Okay, and again, it's not the code that I'm talking about, but like these invocations here, and just using the sort of OO terminology here. Okay. All right, so suppose that the timeline went a little bit differently, right? That the background task is a little bit longer, right? And the user, clicks in the middle, right? That's exactly where, this bug originally happened, right? Is that if you just have the click listener and you have execute, then, you have two executes, and then this is where the exception happens, right? You can't call execute on the same async task. Right? So seeing this picture, right, it suggests a very natural sort of bug fix. And roughly the bug fix is pretty close to this, right? Is, just obviously simplified for presentation, right? Is that, well, then that click handler is disabled, as soon as it happens the first time, right? So that you can't actually realize this particular trace. Okay? All right. So that leads us to this idea of talking about realizable message histories. That is, if we think about like some sort of ghost state or hidden state, right? That the framework has some set of callbacks that are enabled for it to call, like the listener on-click at the beginning. Right? And the application simultaneously has some set of call-ins that it's allowed to make. Right? So like async execute is initially allowed, right? And then afterwards, after the async execute, then there's a new enabled callback, the on-post execute. Right? And then afterwards also, it's no longer allowed to call execute, otherwise an exception would happen. Right? But it can also call button disable, right? And then maybe it calls disable, right? And that's the bug fix, right? And then that sort of disables. Oops, it disables the sort of on-click callback, right? Okay, so flipping that sort of crossing out, right? Okay, right. So then, so this model state that's behind the scenes here that we've sort of thought about here, right, is that the enabled callbacks model what the framework may invoke next, and the allowed call-ins model what the application can invoke without error. Right? So if we look at this message history, this sequence of messages, right, this defines the observable interface between the framework and the app. All right, so then, we took this idea and did a bunch of others. I mean, in fact, at the time we were looking at dynamic analysis, we were detecting life state races. We called this idea of, callbacks and call-ins by analogy to type state life states, right? And we were looking for such races, right? So you can see the paper for those details. But what I want to focus on here today is, or mention here is, right, is that really this provides a concrete basis for thinking about goal-directed abstraction, of callback control flow. Okay, all right, check my time. Okay, cool. All right, so moving on. Okay, so again, back to our sort of Android is craziness picture. Okay, so again, let's sort of, by magic, poof, all that sort of other complexity is gone, right? And just again, go back to the assumption that this is a sufficient model to work with. And also, let me simplify for discussion here, to start, right? That let's just focus on proving, dereference is safe. Right? That is like, some sort of nulling out, which actually is quite common, right? That at the destroy, you might need to null out things to make sure you free resources and not have memory leaks. Right? And then that we're focusing here on that, is a particular given dereference safe. But even in this much, much simplified model, right? You still have life cycles and many different kinds of components, and all the callbacks can interleave, right? So the challenge here is that verifying safety of dereferences depends on callback interleaving. Right. And we have multiple components. Well, they interact through some shared heap, right? They operate over a shared global heap. And so the challenge in verifying the safety of dereferences is that it depends on the ordering of heap rights. Right. But going back to our picture, if we care about just one dereference, that the safety of a particular dereference shouldn't require reasoning about all callback interleavings, right? A small goal-directed analysis could consider just the relevant ones, right? So how do we be, smarter? Right? Okay. So the core idea of this work that I'm pulling out for the sake of today, right, is that the idea of being able to jump back to relevant callbacks. That is, if I look at my components and I have one, and care about, one callback where, there's some safety property that I want to prove here in that one callback, right? We can find the data relevant callbacks over approximately that sort of modify the sort of field that we care about in question, let's say. Right? And then, so that sort of filters out and drops a whole bunch of stuff as being irrelevant. And then, of course, there's still some things like the destroy that we don't want to visit, as being relevant. So maybe we can somehow filter those out using some notion of control feasibility, right? That it's after the click, it can't be backwards reach from this click. Right? So what we end up here is with a backwards analysis that sort of jumps between different callbacks. Right. And again, still, like, we've thrown out a whole bunch of the program. The rest of the program is irrelevant. We never even really thought about it with respect to the sort of callback control feasibility bit. Okay. All right. So this data relevance, right, bit, right, let's look at it a little bit more, right? So, of course, this is like, if we start out with just the transition relation of, a system, right? Given a current location, we output the next locations that we sort of need to visit in our analysis. But if we replace that with a relevance relation that has input also as the current query we're looking for. So that is, maybe we can do this in two steps. One, which is, well, first, we look at the sort of data relevant locations to the current query. We identify locations that can write to the query queue occur. Right? We can compute this using some sort of pre-pass points analysis or types or field-based or whatever, right? However approximate. And of course, this is a very classic idea, if that's not particularly new, right? That we can follow data dependencies instead of the control dependencies, right? Which yields a sparse analysis. Right? But here, this is completely flow insensitive if I just sort of took this as my sort of next locations to visit perspective. But if we add a filter on top of this, right, we selectively get back some sort of flow sensitivity that we want. And we can choose this at every transition step. We can decide, if we want a different sort of thing, right? That we can filter the set of data relevant locations using control flow and the current program point. Right? That is, if we have this control flow graph, right, we can filter out the ones that are not backward reachable from the current location. And we can also filter any locations that are post-dominated by other relevant locations, the other ones that we choose, where we must visit first from some other location. Right? Okay? But of course, I kind of hid something here, right? Which is in order to have such a picture to do that filtering, I'm sort of essentially assuming some sort of static control flow, right? And in the case of Android, some static callback control flow. But this does become a basis for this sort of targeted modeling idea. Okay, right. All right. Okay, so now we can dive in there. Okay, about abstracting message histories. All right, let's go back to our original picture, right? Like, let's try to, verify this fix. Okay, so I'm switching a bit to the sort of more modern version because that code is a bit simpler and easier to read, so compared to the async task code, right? But we're going to actually look at, trying to follow the reasoning to get to this fix. Okay, all right, and only model those relevant missing transitions. Okay, all right. So if we zoom in on the stack trace, just really show you that this is the only app code in the whole stack trace, the only thing that has antenna pod in there, right? Is the callback to call. I know, slightly confusing for our presentation, but the callback is called call. Okay. Okay. All right, so that's the first bit, is that, okay, we have to think about there's error somewhere in call. Right? All right, so let's click on the, fix. And see a bit of the fix. Oh, this is the change. Okay, there's a change that something about unsubscribe. A call in is made in the change this edition. Right. So the fix here is that calling the call in unsubscribe somehow is the fix. And then if we sort of like read a little bit more about call in and unsubscribe, we learn a little bit. Like in the summary here is that the callback call. F.call for some F, or for all F, only happens only if, there has been some call in of subscribe on that F, right? Has been invoked somewhere in the past, and the S.unsubscribe has not been invoked since, right? For all Fs and for some S, and I'm trying to get a little bit more precise now. Okay, all right. So what we're going to try to do here in like 5 minutes, hopefully, is like, can we verify this fix with just this one key targeted callback control flow model? Okay, so let's do this backwards, goal-directed reasoning, right? Okay, so we're going to interpret backwards from the error goal in the callback, right? So here's a snippet of that call code. With some, simplifications, I suppose, but basically there's some use of this activity field, and I'm going to represent it as this assertion that the activity better not be null. Right? Okay. So at program location 4, I'm showing sort of the starting goal, which is that there's some sort of abstract message history. I'm going to call OKHist here. And then what we want to do is suppose, for the sake of driving a contradiction, that the app can reach here, this location 4, using any realizable message history. That's what I'm representing with OKHist, and with the error condition that this activity is null, which I'm making a little bit more explicit here with this kind of separation logic bit. Okay. Right. Okay. And what I want to say is that this OKHist, well, the concretization of it is that it concretizes to all realizable message histories. So it's a sort of top-like thing, but not quite. In the sense that this realizable says, well, it depends on whatever the underlying targeted modeling that I'm going to do now or later. Right? Okay. Now if I just go backwards to, then pass to the beginning of call, back into the framework essentially, right? Because now the program location that really is, before call is inside the event loop of the framework. And what I'm saying here with this assertion is that suppose that the framework can reach here, the framework location, using a message history where appending the next callback, the f.call, is realizable, and with f.activity being null. Okay. And this is like what we're writing here with this ordered linear implication, kind of on the right, to represent. And I'll sort of dive into like what that is a bit, right? Because it's like, oh, what is this appending this thing? Okay, all right. Okay. So what is the meaning of this sort of appending, thing? Is that, okay, so it sort of concretizes to a bunch of concrete message histories. Okay. Now I'm sort of a little bit, for the sake of slides, a little bit, being loose here, right? Well, really, I mean like some concretization of a possible message, right? So if there's a concretization of this abstract message, then appending that sort of concrete version of that abstract message is in the set of possible realizable message histories. Okay. All right, let me give some examples. So suppose that OKHist, or a set of realizable message histories based on whatever background model we're working with, looks something like this, right? So one of them that we've already thought about, right, is that there's some subscribe and some number of calls, and then eventually call happens. Right? Okay. Of course, I could also have a different number of things before call or after call. That's these different dots. Okay. Or some prefix of that, right? Like I got to the subscribe and I haven't yet gotten to call. Right? Which of course could also include kind of the empty sequence, right? That empty message history. The empty history is for the initial history, for the framework, main, right? Like, oh, the framework hasn't started yet, hasn't done anything yet. Right? Okay. All right. So then what we're doing here is essentially filtering out some things, right? Is that, well, the next thing to be done is call. And so that's sort of like, that's one that's allowed that we keep, right? That is also one that we allow and keep. But the other ones don't end in call, so those are ones that we're sort of throwing out, at this point. Right? And in fact, the initial history is excluded, right? So what this is saying is that, oh, we can't just, start here in the middle where call is the next thing. Okay, so, in short, in summary, right, the abstract message histories constrain the past with what's necessary to reach the goal in the future. Right? Okay, with these constraints. Okay. All right, so that's as technical as we're going to go today here, right? So to pop back up a little bit, right? So then, to kind of finish the verification, right? The callbacks that are relevant to this particular assertion, right? Well, there's this destroy that does that unsubscribed, so that we saw there in the bug fix, right? This is relevant, because the f activity is nulled there, and actually because unsubscribe is related to call because of that model. So, but if we, walk through high level what the verification would continue is, right? If callback f.onDestroy comes before the callback f call, then unsubscribe must also come before, contradicting the model. The other one that's relevant is the create callback, right? So, but there, if callback f.onCreate comes before callback f call, right, without destroy in between, then now the f.activity is non-null, contradicting the constraint that f.activity has to be null. So at fixed point, if the backwards from error invariant of the framework location framework excludes the initial message history, that sort of empty sequence, then the error condition is unreachable. And it's a little bit interesting to observe, right? It's not that we have a contradictory state here at this point, right? The concretization is not empty, it's not bottom. But it excludes the initial message history, and that's where we're deriving this sort of contradiction. Right? And this sort of excludes initial is that, well, you can't start the framework in the middle, right? That's just, the framework can't just be in the middle of the sort of like sequences of that are realizable. Okay. All right. So, so this notion of checking excludes initials and intersecting abstract message histories, and then being able to specify those models, right? Using a restriction of first order pastime LTL using SMT. That's what's talked about in our upcoming UPSLA 23 paper. That's going to be given by my student Sean Meyer. So if you're still around this week, I encourage you to look at more of the gory details. All I've done here is kind of set up the problem, right? And he's sitting there in the back as well. All right. Okay. So of course we want to know, does this actually work, right? Does targeted modeling enable distinguishing the fixed versions from the buggy versions using our tool Historia in real callback enabling issues? So So what we did is we pulled out 5 fixed issues, changing some enabled callbacks. So we didn't even consider anything that are like simple, easy things to prove, right? Things that actually require changing the set of enabled callbacks, right? We got them from 2, pretty like well-developed apps, right? AntennaPod and ConnectBox. They have lots of stars, whatever. And then we tried to compare it with, the sort of no modeling pragmatic approach and the upfront, lifecycle models. So here's the net, summary, right? So here are those 5 issues in the buggy and fixed versions. Right? Here is the number of relevant callbacks and call-ins used. So if you think about all possible interleavings of this, and then if you have things like this or multiple instances, right, that sort of thing, that's a big number. And then we compared it with using the sort of no order pragmatic approach, using infer, and we had to do a little bit of things of like some of those illegal state exception things. So we had to sort of rewrite it to be for the purpose of doing null dereference checking that infer can do. And so we get alarms on all of them. Right? And then we compared it to using the sort of upfront modeling of trying to write down the model. Note, we're not using the flow-droid analysis tool, but just the model that it generates, which is sort of the most well-known sort of Android analysis tool out there, doing some sort of lifecycle modeling, right? So, but then we sort of looked at the model that flow-droid would generate, and then thought about like, could any possible analysis, no matter the precision, be able to, prove or, and such, right? And this is, the result. And then we did our sort of target modeling approach of writing those little specifications of relating, for example, subscribe and call, right? And of course, this is the bottom line result, right? That all of the instances were able to be correctly distinguished, and that's the challenge, right? Between distinguishing the buggy and the fixed versions, right? Whereas the other tools either alarm or prove or something like that, but never distinguishing the buggy and fixed versions. All right, and these are the number of, those little, that sort of, that pastime LTL type formulas we need to write, the number of specifications, that kind of targeted modeling, and here's the verification time and the depth. And so we're able to prove these without going too deep in terms of the number of callbacks that we need to go down. Okay. All right, of course, now we just picked out 5, well-crafted things. Of course, we're going to get, like, that's good, right? So is this sort of generalizable? Does targeted modeling generalize to prove assertions on real-sized, complex, widely used Android applications? So what we did is go to the sort of open source repository of Android apps called F-Droid. We picked like apps that were, we just basically based on apps that were well-maintained sort of things. The proxy being that they've been updated in the last 2 years, and the project was started a long time ago, updated more than 8 years ago. We end up with these 47 apps and 2 million lines of code, right? Then from that, we took those 5 bug patterns from those 5 issues and wrote some detectors to find those, and we ended up with 190 possible error locations. Okay. And let me just put the bottom line summary here, right? And I'll give you the table here. That without modeling, without any modeling, we were able to prove 43% of them. So if you will, those are the easy cases, right? 28% alarmed, right? And then 29% sort of timed out within an hour. We sampled 8 of those alarms and tried to verify with targeted modeling. Right? And from that, we were able to verify 3 of them with just 4 little specs. We found 1 true bug with just 1 specification, and 3 did timeout in the sort of 1 hour we gave it, and we also gave ourselves a timeout of being able to write down the specification, figure out what we need to write down in an hour. So 1 timed out of we got tired of figuring out, what's going on, some sort of thing. Okay. All right. So popping back up to the key ideas, right, that we first thought about how do we talk about just the application only? And then if we only have the application, how do we jump between relevant callbacks? And then how do we actually do some sort of targeted modeling to be able to prove cases where the callback orderings do matter. Okay. All right, so to pop up into kind of the take-home message. Right? So one is, maybe be goal-directed. That reasoning backwards from goals enables enables relevance and sort of distinguishing relevance and irrelevance. And a sort of call to arms here, and the second bit is like, come together. There's no such thing. There is no program analysis, only app analysis. And we somehow have to abstract the interface, with its framework and design abstract domains around that. And okay, let's see. If I may, just kind of also call to arms and plug sort of the next thing we're thinking, right, is that, if we think about that sort of main picture of like, okay, my clicker died. Oops. That, can we, instead of manually modeling those missing transitions, can we do synthesis and synthesize those? That is, maybe, can we complete a given transition system consistent with maybe some additional goals? Okay. All right. So with that, I'll take some questions and show off the beauty of Boulder to invite folks to visit, students, postdocs, collaborators, and so forth. Yeah.
Questions? Well, okay, I can start with one. Could you maybe give us an idea of the kind of abstractions that are involved in this kind of work, like abstract domains, or I saw some separation logic here and there, but maybe a bit more.
Yeah. So the assertions, like I showed, there's, we essentially model the heap using separation logic and such to talk about what fields that could be possibly written and track those precisely. And then the sort of abstracting of the message history is kind of the domain that we've been essentially working on to talk about how do we represent the interface.
Thanks. Other questions?
Thank you. Great talk. If you were made a dictator of Android and you could design the API with kind of a view towards program analysis, could the problem be made easier, or is it just inherently difficult?
No, I think that's an excellent question. Of course, some things could be made easier, I suppose, right? But I think there is an inherent difficulty into the fact that you don't have all the code, right? That and there's really not, every framework has, every framework for an interactive application ends up looking like this, right? You write some small bit of code that hooks up to it in some way, and that's, I think, the fundamental program analysis challenge is that we just can't go with this sort of given the whole program sort of perspective. So
we have time for some other questions. I don't see anything. No? Well, I have
one more back there.
Sorry, I didn't see.
Yeah, so I'm kind of curious, because you have one slide you show that you are sampled 8 alarms, then you try to verify with target modeling there. I'm curious, you mentioned you with 4 specifications, and you found the true-backs in 1 specification. So how do you get those specifications?
Right. So this is this notion that the specifications are ones that we wrote, or Sean wrote here, by essentially consulting the Android documentation or understanding just like a developer would. So essentially, we are very much essentially trying to capture the developer workflow here, right, in the static analysis, right? That like, oh, there's a crash here. Like, how do we check that it's safe? Now, a normal developer probably reads the documentation and sort of convince themselves, mentally through that simulation. We're taking that one step further and taking that sort of mental simulation out into the static analysis and doing that sort of understanding of the documentation and codifying it into a temporal logic formula, essentially.
Okay, so yeah, another question is, programmer usually they read the code, they never read the specification. So I wonder if there are some alternate ways to derive those specifications.
Yeah, no, of course that's so the question is, could we automatically derive the specifications? And of course that's, I think, a promising thing we of course want to explore in some way, right? And that's kind of what I sort of alluded to in the next steps is, could we synthesize those specifications subject to some other higher level specification, like, what are possible, what are goals, right? What are the other goals in the program that need to be either satisfied, either be reached or unreached or something like this, or unreachable, or proven unreachable. And I think that's potential, right? Now, one thing, of course, that any of these specifications that get written are reusable for the particular version. Right? And I would also say that it's essentially like, there's always this like, oh, like, but we have to specify something. Well, you always have to specify something, I guess I'm calling out. Like whether it's you specify the whole Android framework up front and complete the program, or whether you can specify bits and pieces that are relevant to the particular assertions you're trying to prove. And we feel like we can get more confidence by doing this sort of targeted approach.
Thank you.
Yeah.
Anything else? Maybe, so you talked about Android, but this kind of ideas also apply to other languages and other kind of applications, right?
Yeah.
So can you say more about this? If it,
Yeah. Yeah, and again, I think we got sort of heavy into Android here in terms of like Vanessa's questions, like could we just make it better, right? Can we just change the framework? And I think it's fundamentally something that if you want to write interactive applications, you're going to have some framework, and I think they apply equally. Now, we haven't looked as closely into others, but we really think of Android as just a model that we can get access to, in the sense that there's open source applications, and it's a complex open source framework that we can learn from. Right. So
thanks.
Yeah. But yeah, I think it applies equally to JavaScript or React or whatever, all these different challenges.
Okay, well, I think we can thank the speaker, and the next speaker can set up.
Thank you very much.